Let's do some Boolean algebra. We are checking to see which Boolean expressions are equivalent. We have A, B, C, and D here. One way to do this problem would be to simplify each expression using Boolean algebra identities to see if they just happen to be equivalent, exactly the same, that is. But another productive way to do it, even if you're under a little time pressure, is to build a truth table. So I'm going to build a truth table here with my favorite order of putting the pairs of values. So left column is my column A, and this is the column B. We could possibly have a false for A and a false for B. We could also possibly have a false for A or a true for B, etc. Okay, so we have columns A, B, and C, D here, or rather answers. I'm just going to label this grid in that way. And one at a time, I'm going to plug in these ordered pairs into these expressions. So plugging in the first 0, 0 for A. Real quickly, 0 or 0 is 0. The not of 0 is true. Plugging in 0, 0 for solution B. 0 ANDed with anything is always going to be 0. So those are not equivalent. I already know that A and B are not equivalent because the simplification with 0, 0 alone makes the one true, A, and B overall comes out to be false. So keep that in mind. I'm now going to continue with plugging in 0 and 0 into C and D in case they happen to be equivalent to either one of these. Well, 0, 0 plugged in to the A and B here in C. The not of 0 is 1. The not of 0 is 1. 1 ANDed with 1 is the same as 1 times 1, which is 1. The not of that 1 is 0. So C overall ends up being 0. So possibly columns answers C and B are equivalent, but we have a long way to go yet. D, plugging in 0, 0. 0, 0 there. The not of 0 is a 1. The not of that 0 is a 1. 1 ANDed with 1 overall is a 1. So D comes out to be 1. So right now we have no insight as to what the final solution is going to be. But I was able to real quickly rifle across there and with my 0, 0 plugged in solution to come up with the overall solutions. Okay, so I'm going to go much more quickly here, assuming that you can already evaluate these expressions. Plugging in 0, 1 for A, 0, 1, that's 1, not a 1 is 0. Plugging in 0, 1 here. That's a 1, that's a 0, 0 times anything is 0. Plugging in a 0, 1 here. That's a 1 overall, ANDed with a 0. Overall inside there we have a 0, the not of a 0 is a 1. And plugging in a 0 and a 1 here. The not of a 1 is 0, 0, ANDed with anything is overall 0. So far, possibly column A and column D will end up being equivalent. I have a feeling that if there is a pair at least of A, B, C, D that are equivalent, it's going to be A and D. Okay, we don't have much more work to do. I'm going to, again, try to go quicker here so that this video isn't so long. Plugging in my third ordered pair over here in my list, the one with 1, 0, using green perhaps. 1, 0. Oh boy. I hope a second ago, because the B is first here and the A is second, I hope I didn't just quickly plug a 0, 1 in. Well, it doesn't really matter because OR is commutative, and because they were different, one or the other, it comes out, it doesn't matter. Anyway, I'm going to be really, really careful right now because that's a little tricky for the person who made this question to have listed the B first instead of alphabetical order A and B when it really wouldn't have mattered. So plugging in a 1 for A, carefully there, plugging in a 0 for B, 1 or 0 is 1. The not of 1 is 0. So we do get a 0 here. I'm just going to slide over to D and plug 1, 0 into D. Plugging a 1 in there and a 0 in there. The not of a 1 is 0 overall. The not of a 0 is 1 overall. And this 0 ANDed with that 1 is 0. Wow, that's a match. I don't think the contest organizers, well, definitely B and C are already out. I'm not wasting my time evaluating B and C. Oops, sorry about that. So moving on then to compare the last ordered pair, 1, 1. 1, 1, plugged in for my A and B here in part A, and then I'm going to only look at D. So plugging in 1, 1, a 1 or a 1 is a 1, the not of a 1 is a 0. Plugging in 1, 1 here, the not of a 1 is 0. 0 ANDed with anything is 0. So we have a match. These two columns are equivalent based on this extended truth table that I just used. We didn't really have to consider the rest of those evaluations. I'm going to list my answer as A and D, because that's what the contest organizers here that made this old test question would have wanted. Which of the following are equivalent? A and D. I'm just listing the letters because that is allowed. Erasing this scribble here and moving on to exercise 2. Now, if you get a different answer, email me, contact me. There's a 1 in a 100 chance that I was wrong there. Number two. Oh, we have different notation. Notice that up here in number 1, nots, ors, and ands were being used as Boolean operators. In number 2, it's using different notation. There are lots of different notations that you might see in high school or college, or maybe even out in the real world of formal logic. So this set of operations is notated where the star means and, the plus symbol where it's being used is the same as the Boolean or operation, and the tilde is equivalent to the word not. So if you're better at using ands, ors, and nots, you could translate all these into that notation, or you could just keep it in this notation. Now for this video, I'm going to keep it in this notation, but maybe elsewhere you can seek out help if you have trouble translating or knowing that they're really equivalent just with different symbols. So again, I'm going to use an expanded truth table. I'm quickly going to count in binary. That's the number 0 in binary, 1, 2, and 3. Put that leading 0 in there, and I covered all 4 possible ordered pairs with Boolean expressions A and B, where they would be either false or true apart from each other. Okay, letter A gets its own column here in my expanded truth table. Possible choice B gets its own, and same for C. Now let's just plug and chug. Plugging in 0, 0 here. Well, look at this. 0 times anything, doesn't matter what this is overall going to be 0. Same here. 0 times anything is 0. In other words, false ANDed with anything over here, whether it's true or false, is 0. Now that is a Boolean algebra identity that I could take the time to show you on a list somewhere, but it's just like math. 0 times anything is 0. It's the annihilation property or something, the zero identity property it's sometimes called, I think. Anyway, it's all 0. And also over here we see that 0 times anything is 0. So all of these end up being 0 in this first ordered pair. Now, where this A is 0, they're all going to be 0 for the same reason. So far, all 3 of these are equivalent so far, but we still have 2 more ordered pairs to consider. So for some reason, I just decided to switch to the color red as I get ready to plug in my next ordered pair to these 3 possible candidates. Okay, so 1, 0, where A is 1 and B is 0. So plugging carefully the 1 in for all the A's, plugging a 0 in there for that B. We work from inside the parentheses out. The not of 1 is overall 0 there. And this 0 for B plus that 0, overall, inside the parentheses there is 0. That not applied to that 0 makes all of this simplify to a 1. And this 1 times 1 is overall 1. So all that work just to know that I can put a 1 right there in my expanded truth table. Okay, over here, B, plugging a 1 in and a 0 in. Again, looking at this ordered pair right here. The not of that 0 must be evaluated first, which that would simplify to a 1. And 1 times 1 is 1, and so B is a 1. So far, they're equivalent. C down here, C. Plugging in the 1 and the 0 carefully. That's a 1, that's a 0, that's a 1. Working from inside the parentheses out, sorry, that's a scribble by accident. The not of B, the not of 0 is a 1, plus this 1, you don't say 2, that's not legal in Boolean algebra, but 1 plus 1, a true, ordered with a true, overall is true. And that was all inside the parentheses here. We now have to apply this not operation here. The not of a 1 is overall a 0, and this 1 times that 0 overall makes C, in this case, a 0. So C is out. It's not going to be equivalent to A and B. I don't even need to consider what happens here, saving time if this were a test situation. And I'm now going to plug in this last ordered pair, the ordered pair 1, 1. And here goes with candidate A, 1, 1, and 1. Okay, the not of 1 is 0. This 1 plus that 0 overall inside the parentheses here is a 1. The not of that 1 is a 0. And 0 times anything over here, which happens to be 1, is 0. So that is 0. And now we just have to plug things into this short expression. 1, 1 being plugged in here. 1, 1. And the not of 1 is 0. 0 times this 1 overall is 0, and they are equivalent. So A, column A, and column B, which of course represent these Boolean expressions, they are equivalent because in all situations, whether it's originally false, 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 true, true, false, or true, true, they come out the same no matter what's plugged in as an ordered pair. So they're really the same thing. It's kind of like saying the answer choice A is the number 2 and B is 4 divided by 2. Well, because 4 divided by 2 simplifies to 2, a lot of times a math teacher or professor would say they're equivalent. They're expressed differently in a different format, but really the values are the same. So A, the value there in all situations is the same as the underlying value here in B. The answer to this exercise is AB. Contact me if you disagree. And last of all, number 3 here. It looks like it's pretty complicated, but now this is, again, you could try to simplify all 4 of these using Boolean algebra expressions, but Boolean algebra identities, I meant to say. But I'm just going to use a truth table. Now, in this case, it's really complicated. It's going to take a long time. This might be a situation where you would want to try to simplify these. And you know what? I'm going to do that. I'm going to simplify a little bit and then possibly use a truth table. So looking at A, A has a situation where De Morgan's law can break up that set of parentheses. So De Morgan's law says that when you have not of something in parentheses with a plus, that this plus here changes to, in this case, a star, because that's the opposite of plus in Boolean algebra. And this not applies to the A term directly. So the not of that A is simply written as not A without any parenthesis there in between. And this not flies over here and applies itself to the not B. So if you originally had a not B here, and then you're bringing this not over, you really have a not B. And you should be careful to add a set of parentheses there because, well, that's the rule when you're being careful. And this is now equivalent to this without those outer parentheses. Now I still have this plus a plus b there. And you really have to be mindful of the order of operations. Because all of this originally did have a grouping around it, you have to keep the grouping by adding this outer set of parentheses here to show that that's really multiplication and that this is addition and needs to stay lower on the order of operations. Well, the next equivalent rewrite here would be to take this not, these two knots cancel each other out according to one of the Boolean algebra identities. And this not a times that b, well, that's still there. And then this plus a plus b, those are still there. So in a way, I did break this a up into something a little bit simpler. I'm going to label this now as my choice a here. And it may or may not happen to already be spotted as being equivalent to B, C, or D, but I'm just going to keep this notation here. B, I'm going to try to use Boolean algebra identities to break it up using the color purple. So here's B, A, not B. That's really the same as saying A times not B. They don't have to, but there's really implicit multiplication in between the A and the not B there. Plus the not of B times A, where there's a set of parentheses that not is applied to. So be careful with this, because this is tricky if you were to try to simplify this further using Boolean algebra identities. Here's why. This is a plus here. So I just took B and I just rewrote it in a way. This right here is a situation where you have to use De Morgan's law. To break this up in the way that, well, you have to do these kinds of exercises, this not distributes to the B and to the A term, but this symbol in the middle needs to change to a plus. Just like up here, that plus changed to a multiplication. In this case, it's the opposite, and but it's the same idea, De Morgan's law. Because that was grouped originally, you technically should add parentheses, just like we added a set of parentheses here to be safe. Now, it may or may not matter, but it's just being safe. I'm going to rewrite this part of the expression. We did not apply De Morgan's law to anything over there. It only applied to this part. Now, this multiplication must be performed first before this addition. Just saying. And right now, I've got a situation where it doesn't really look equal. Oh, this is interesting. Well, no, it's not interesting. This is just what I have left. I'm going to label this B. And at least I did, these parentheses were broken up. I added parentheses, but you know what? They're not really needed as long as I know the order of operations. This multiplication is done before these parentheses. Boy, this isn't seeming to help me out at all. It's wasting a lot of time if this were an exercise on a test. C, to break this up. C. Well, this is a situation where we have De Morgan's law inside of a situation where we will need to use De Morgan's law. So rewriting the outer set of parentheses there, and this not applies, distributes to that A, the not here distributes to that B, but this plus changes to a star. I still have one right parenthesis there. So this is C. I just simplified using De Morgan's law on the inside there. And now I really don't see anywhere else I can go with this. Yes, I do. Like I said before, we could apply De Morgan's law to the outer set of parentheses. So this not A, actually no, because of that term A, it doesn't apply directly to De Morgan's law. De Morgan's law is only when you have simply a not that you're distributing. Here, this would be just normal distribution. So not A times this term would be not A times B. Remember, this is a plus here. The not A times all of this would be not A times this not A times this not B. By one of the Boolean algebra identities, if you have two things being multiplied, it's the same as just having one copy of that term. So this right-hand side here could be rewritten this way. We still have, this is really multiplication here, by the way. If you want to look at it that way, you can put the star in there, and then we still have a plus. Well, this is interesting. There is a Boolean algebra identity that speaks to this. Anytime B is if B is false, then all of this is 0, and 0 plus all, actually no, I don't want to explain the other Boolean algebra identity. I'm going to use a different one instead. I'm going to factor out the not A. The not A term can be factored out. The B is left here on the inside of a new set of parentheses. That plus term is still there. Factoring out the not A, I'm left with the not B there. So now that I've factored out that not A, I see that B plus not B. There is an identity that says that no matter what B is, whether B is originally true or false, one or the other of these is going to be true. And a 1, a true, plus anything is always overall 1. So it's like not A times 1. We already know that it's going to work out to be that way. And not A times a 1, anything times 1 is whatever that anything is. So C can be simplified to simply not A, which to me does not look very equivalent to these two, but I'm sticking it out. I'm still not sure. So real quickly in this long video, D, I'm going to try to simplify D using Boolean identities. The not A times not B is written without a star there, but I guess that's okay. Times not A plus not A times B. Now I can factor out the not A. And if I factor out the not A, we're left with not B here on the left plus just B, which we just saw a second ago simplifies to 1. So 1 times this not A overall simplifies to not A. Well, I'll be darned. Look, this simplification of exercise D, choice D rather, is the same as the simplification of C. So I already know that C and D are definitely part of my answer because they're equivalent. That doesn't straight up tell me that A and B are not possibly parts of the answer. So using the color black here, I'm just going to plug in a 0, 0, one of my ordered pairs for 0, 0. I'm going to plug those in to A and see what that simplifies to. 0 plus 0 here is 0. Hold that to the side. 0 plus the not of 0 is really a 1 overall. And the not of that 1 is 0. That 0 plus that 0 is overall 0. Interesting. So for choice A, a 0, 0 ordered pair is 0. Now let's plug 0, 0 into either C or D since we already know they're equivalent. So where the A is 0, the not of that 0 would be 1, which is not what C just worked out to be. So I know that C is not equivalent. I'm sorry. I was talking about A. By plugging 0, 0 into A, I know that A is not one of my solutions. It's not equivalent to either expression C or expression D. So that was a quick analysis to rule out A. And now let's just decide whether B is a possible part of the answer or not. Again, let's plug in the 0, 0 here as an ordered pair. 0 times the not of 0 is overall 0. Plus, working inside the parentheses out, 0 times 0 is 0 in there, but the not of that 0 is 1. And 0 plus 1 is 1. So B simplifies to a 1 when 0 and 0 are used as an ordered pair. I'm going to take this value for A, plug it in here. The not of A is true. So B is still in the running to possibly be equivalent to expressions C and D. So let's not, let's do plug in the ordered pair 1, 0, 1 and see what happens there. And see if B is also possibly equivalent. So if we plug in the ordered pair 0, 1 here to B, the ordered pair 0, 1, I'm going to use blue, the ordered pair 0, 1, a 0 plugged in for A, a 1 plugged in for B, 0 times the not of 1, well that would be 0 times 0, which overall is 0 here on this side, plus plugging in, oh, be careful here, the 1 needs to be plugged in for that B, the 0 needs plugged in for A. Well, anyway, 1 times 0 is overall 0. And the not of that 0 is 1. And this 0 plus that 1 is overall 1. So here in this column for B, we get a 1. We get a true, that is. Now let's plug 0, 1 in to either one of these two, C and D. Well, A is 0, and the not of a 0 is 1. Ooh, so right now, B is still in the running to be equivalent to C and D. Let's plug in, oh, sorry about that. Let's plug in the, ordered pair 1, 0. So plugging in the ordered pair 1, 0 in expression B. Some of this you could probably do much more quickly in your head if you didn't have to explain it like me and write it out in a video. So please go as quickly and surely as you can if this were a test exercise. Nonetheless, plugging in 1, 0 here, a 1 for A, a 0 for B. The 1 times the not of 0 is overall 1. 1 plus anything is 1. So we get a 1 there. This is nothingness. And plugging in the ordered pair 1, 0 here for my not A, or this not A, it doesn't matter. The not of 1, let's see, the not of 1 would be a 0, and 0 is not the same here as this 1. So we finally eliminated B as one of our possible solutions. So the answer indeed to this exercise is C and D. Contact me if you disagree. There's a chance that I made a mistake somewhere. Good luck. Whether you use the method of simplifying the given expressions a little bit and then using a truth table, or using a truth table from the get-go to evaluate if given expressions are equivalent or not.